Hello everyone, my name is Aidmar Wainakh. I'm from the Technical University of Darmstadt, and I'm glad to introduce you to our work on enabling privacy-preserving rule mining in decentralized online social network. So starting with online social network, which is actually start or become a prominent part in our modern society, so millions of users using it on daily basis. And there are several services there where users provided with recommendations on new friends, new articles, new songs, and so on. And all these recommendations actually generated by recommender systems, which are built using a variety of data mining and machine learning techniques. In this work, we are focusing on one technique, which is association rule mining, and I will explain it in a minute. So currently, the dominant actually online social networks are based on centralized approach, where the service provider collect all the data of the users and apply variety of analytics techniques in order to build the recommender system for other also purposes. However, with this scheme, actually, the issue that there are several data breaches and privacy violations, and this is come as a result because, for example, the service provider control the data of all the users, and they are not providing enough information about how they deal with this data and process it. So we have lack of transparency, and they failed in many occasions to protect this data. And this is evident by actually many data breaches, and we saw this in the recent few years in many headlines. To mitigate these issues and concerns, actually, researchers and activists propose a decentralized online social network, which is mainly based on peer-to-peer networks. So we distribute the data, and it's not stored by a central entity anymore, but it's more on different nodes in this peer-to-peer network. And with this social networks, actually, the social networks try to provide more information and more transparency about how they function and empower the users with more means of control. So the users might change or might select where to store their data. However, with distributed data, it will be more challenging now to apply analytics and improve the services. And that's what we are trying to answer in this work, how we can apply association rules as one analytic technique in the decentralized online social network. So what is association rules? It's mainly captures the relation between items, and items here you can see it as the topics or interest of users. So we can see here some examples in this table with a binary representation. So either the user is interested or not interested in these different topics. So to build the rules, first we look or we try to build the frequent item sets, and this item sets which are, and this is the item sets which are frequently observed together. So like in this example, we notice that privacy and GDPR were observed several times together, and that's why we can have a frequent item sets, and based on this frequent item sets, we can build a rule says if you are interested in privacy, so you might be interested also in GDPR, and based on this rule, we can provide you with some recommendations. When the data is distributed, so this is a well-known problem also in the research community, distributed privacy preserving association rule mining, where we have multiple parties, and these parties do not want to disclose their data, but still would like to build the association rules together. However, all the solutions in the literature actually consider a limited number of parties, so it's not designed for larger scale applications, but for data centers where the number of these data centers actually is limited. And this solution is mainly based on cryptography. So using encryption primitives like community encryption, secure multi-party computation, elliptic curve, and so on. However, all these actually solutions introduce a high communication and computational cost, especially for large scale applications, and use a priori algorithm to build the frequent item sets and the rules, which also require multiple passes through the data sets, which introduce extra overhead. In our approach, we have two steps. The first step, we sample the users based on the social graph via random walks, and then we apply distributed frequent pattern growth algorithm to mine the frequent item sets. So starting with the first step, the sampling. So in our scenario, actually, we have a distributed, we need a distributed algorithm to sample the data users, the user data, as we assume that there is no central entity has global knowledge of the social graph or the data of the users. And that's why we use a random walk, which move from a user to one of his friends randomly selected, and so on. So from user to one of his friend, the issue of this walk that it is bias toward highly connected users. To mitigate this issue, we have the Metropolis Hosting random walk, which introduces the proposal function, and this is works as following. So if we have this example, so the walk actually reached to John, and John now selected Lara as the next candidate for the walk. And before passing the walk to Lara, actually, John calculate the fraction of the number of his friends, divided by the number of Lara friends. And if this fraction was bigger or greater or equal to a random variable, the walk will proceed to Lara. Otherwise, John needs to select another friend. However, in this approach, actually, it's assumed that John knows the number of friends of Lara, which could be a sensitive information. Therefore, we propose the following modification. We propose that John sends his number of friends divided by the root square of a random variable to Lara, which apply or which check the following inequality, which is equivalent to the main or the original proposal function, and send back if this inequality holds or not, a bit 0 or 1. So with 1, John will push the walks towards Lara. In addition, we allow the users to decide locally whether they would like to participate or to contribute with their data into the sample or not, with a probability, contribution probability. And with these two modifications, actually, we calling this approach now Metropolis Hosting Anonymous Random Walk. So we propose applying multiple random walks in the social networks in order to not get stuck in local communities, and the number of walks and the length of these walks are customized parameters in our approach. The last user of each walk called prime user, which will receive the whole sample of the walk, and these then users can apply together the random the rule mining, and where we have two steps, the frequent item sets and the rule mining. However, the frequent item sets actually creation is the dominant part in this process, so it requires more computation, and that's why we are focusing on this part in our work. So after doing the sampling, we apply the distributed frequent or FB growth algorithm. And so this algorithm actually converts the data we see in the table into a tree. And by that, and with this format, actually, we are reducing the computation we need to go through this data sets and create the frequent item sets. More details about this algorithm can be found in the paper. We applied the distributed version of this algorithm, and we adopt the first step in this algorithm, where we are calculating the frequency of every single item globally through all the prime users. And to do that, we use a simple secure sum technique, where the first prime user add a random variable to the frequency of every item. So here we have the sport, and this will be passed through the primary users. Each prime user will add their own frequency for every item, and finally the first user will receive receive the last message and will subtract the random variable. By this, we will have the frequency of sport over all the prime users. So with this, actually, we move to the experiments where we evaluate our method. And here we focused on the correctness of the frequent item sets, and we use the recall and the precision metrics, and we also look at the efficiency, the number, and the size of the messages in the sampling. And we use the three data sets, and due to time constraints, I will look only into the ORCUT and LiveJournal today, and we look at two sample size and contribution probability of 0.5, and we compare with uniform sampling, random walk, and anonymous random walk. So the correctness of frequent item set here we can see the recall and the precision on the X and Y axes, and we can see the metropolis in green, the anonymous metropolis random walk, which outperform the traditional random walk with the anonymous random walk. And we can see that it works even better in ORCUT comparing with LiveJournal, and the reason can be that ORCUT is highly connected network, so the average node degree is 72, comparing with 14 in LiveJournal. So the walks are not actually get stuck in local communities. And seeing also the sample size of 1, we can see that the anonymous metropolis random walk shows highly resilience, that the changes between 20 to 1 sample size is quite limited, while the uniform sampling degraded remarkably. Here in ORCUT, for one sample size of 1%, actually the metropolis performs quite closely to the uniform with average precision of 96. Looking at the efficiency, the number of messages we use or we need for doing the sampling. So we see that the random walk, actually the traditional random walk, achieves the smallest number of messages, and that's expected because all the nodes visited in the random walk contribute their data, and therefore we are reaching the sample size faster than the anonymous random walk and the metropolis anonymous random walk also. Again, we see that in ORCUT we have less number of messages. Again, this is related to the highly connected nodes in ORCUT. So we see also here the proposals, the number of proposals for the anonymous metropolis anonymous walk. And this is the number of messages we are sending for the candidate friends. So before the walk proceeds to the next friend, we are sending this proposal functions and the bit. And this is, we can see that it's considerable, the number of these messages. However, they are all small. The size of this message is quite small, and therefore we assume that they are not providing or not introducing high bandwidth overhead. Looking at the looking at the size of the messages, which we refer to it as a number also of items in the messages. And here we can see that the metropolis actually has less number of, or has messages of less size comparing with the random walk and the anonymous random walk, yet we are achieving better recall and precision. And the reason here that the metropolis actually avoiding the highly connected users, which it was shown in the literature that the highly connected users usually have higher number of items, and therefore actually the walk of the metropolis collecting less number of items is still better quality, or we are still achieving better recall and precision. So to recap, in this work, we mine the frequent item sets in distributed or decentralized online social network using the metropolis anonymous random walk and the distributed FB growth algorithm. We used 3 data sets to evaluate our approach, and we show that users in decentralized online social network can collaboratively mine high quality frequent item sets. And this is related also to 2 factors: the quality of these frequent item sets related to the connectivity of the network and the data distribution. And as an example, we saw that in ORCUT, which is a well-connected network with a sample size of 1, users can reach 96 precision, average precision score. And with this, I would like to finish my presentation. Thank you very much for your attention, and I would be happy to receive your questions.